Hey everyone, welcome to the chemical equilibrium tutorial. Today we'll be covering what chemical equilibrium is and then take it further through real-world examples and calculations. Let's get into it. Chemical equilibrium is when a chemical system has equal forward and reverse reaction rates. Consequentially, the concentrations of reactants and products remain constant at equilibrium, even though the system is in a dynamic state. Imagine you have a box of bees. I don't recommend carrying around a box of bees, but bear with me. Let's pretend there's a wall halfway through the box. So at this state, there's 6 bees on one side and 0 on the other. Now let's say you remove the box. Naturally, the bees will disperse within the box. They won't just all go to the other side though. They will disperse within the box, and there will be a dynamic movement of the bees within the box. Now, at this state, there's a lower concentration in one side, which means the forward reaction is slowing, and the bees aren't bumping into each other anymore. Let's say when they bump into each other, they move more or disperse. On the other side, there's a higher concentration, more collisions, and the reaction speeds up, which is a reverse reaction. This means that eventually, the forward and backward reactions will be equal. One can use the equilibrium constant to understand the concentration of the reactants and products present. The equilibrium constant is a molar ratio of products over reactants at equilibrium and can be shown through K, while the reaction quotient, Q, describes the nature of the reaction mixture. And it can be calculated using the following equation. Notably, the amounts of starting materials and products remain constant at equilibrium, meaning that their ratio, or reaction quotient Q, is a constant value, so equilibrium constant K. Now, to calculate the equilibrium constant, one can use concentration or pressure. If we're measuring using concentration, the following equation can be used, in which Kc will be described in terms of molar concentrations of the starting materials and products. While pressure, we can describe Kp in terms of partial pressures of starting materials and products. In the case that the mixture contains both gases and solutions, one should use relative activities. This unitless measure can be accomplished by dividing the concentration or pressure by the standard concentration or standard pressure, leaving you with a unitless relative activity. Now, if we're working with pure solids or pure liquids, it's a bit easier because the activity of any pure solid or liquid is 1, since the concentration is the standard concentration. So, we can just replace that with 1, and it makes our lives a lot easier. For example here, we see that the H2O is liquid. So when we're writing the K expression, we don't really need to put it over anything because it's just over 1. Now let's take a look at the factors that affect equilibrium. Now remember, reactions occur when molecules collide. So everything that affects these collisions will affect the equilibrium. Let's look at the Chatelier's principle. This says if stress is placed on a system at equilibrium, the system will proceed in a direction that minimizes the stress. For example, let's look at concentration. If you increase the concentration in a system, you are increasing the amount of collisions, and vice versa. Lower concentrations equal lower collisions. Therefore, if you increase the concentration of the reactants, it'll shift right, but if you increase it of products, it will shift left. Now, if we take a look at temperature, it's pretty similar. When you increase heat, you are increasing energy and therefore reactions or collisions, and the opposite is true. Therefore, if you increase the temperature, it'll shift towards the endothermic reaction, but if you decrease it, it'll shift to the exothermic reaction. Let's take a look at how temperature affects the equilibrium constant. When it's exothermic, there's a lower equilibrium constant, while it's endothermic, there's a higher equilibrium constant with higher temperatures. Now let's take a look at pressure/volume. When you increase the pressure/reduce the volume, the direction will shift to the area which has fewer moles of gas, and the opposite is true. Let's quickly talk about the notation for K. Now, this is in relation of K to the balanced equation. So let's say we have a regular equation. We know we could write it with products over reactants. The opposite will exactly be the opposite and can also be written as 1 over K1. Now if we double it, it's the same thing. We just square every one or just square the total K. And if same thing, if we half it, we put it to the half of everything. When we're working with multi-step reactions, we want to solve for the overall K. So let's say this is both in one reaction vessel. And let's say the B has negligible concentration. Well, it could just cancel out and we can multiply the two equilibrium constants together. There are also more shortcuts, like if K is smaller than 10 to the negative 10, it's almost entirely reactants, while if it's bigger than 10 to the 10, it's almost entirely products. Now, when K is that small, there's almost no tendency for the reaction to occur, but when it's that big, there's a strong tendency to go to completion. Another way we can interpret K is to compare the initial Q to K. So if the initial Q is bigger than K, the reaction shifts to the left, while if it's smaller, the reaction shifts to the right. Now, sometimes we know the amount of substance that we begin with, but the equilibrium amounts we don't know. So we can use stoichiometry to help solve, specifically ice tables. Now in these tables, there's an initial, a change, and an equilibrium column. So in the initial column, you write the initial concentrations that are known. The change, you write how much will be changed using the coefficients from the balanced equation. And the equilibrium will be the initial plus the change. These numbers can then be used to calculate the K by placing the products on top and the reactants at the bottom and putting the coefficient in the balanced equation as the exponent. Now you're probably wondering, why is this even important? Well, there are chemical equilibriums everywhere we look, even in your swimming pool. When you add chlorine to your pool, there's an automatic chemical equilibrium reaction that we could take a look at right now. So here's the equation for chlorinating water, and the K constant is 2.8 times 10 to the negative 8. And we know the initial concentrations, let's say 0.2. We don't need to look at water because it's a liquid, and 0.0. By putting the change, we can find out what the equilibrium expression will be by placing over the products over the reactants. From here, we are going to just use simple algebra to try to isolate x. And what you will find is that we will have to use the quadratic equation to do so, which is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Now, if we plug this in, we will get two separate answers. The first option is 7.5 times 10 to the negative 5, and the second is negative 7.5 times 10 to the negative 5. And we can decide which one to use by using logic. It has to be able to be 0.2 minus x. And in this case, the only one that works is 7.5 times 10 to the negative 5. So we can find out the equilibrium concentrations by plugging in x. So in this case, when you plug it in, the equilibrium concentration will be 0.199, and each of these will be 7.5 times 10 to the negative 5. But what happens if we start off with different concentrations? Well, you'll find that with different concentrations, we will still have the same equilibrium constant, even though the concentrations of products and reactants are different. For example, I'm going to try this out by changing the 0.2 molar to 5 molar, and this will change up our numbers everywhere here. So we're going to end up with two different x values now. Once we do this, the first one will be 3.74 times 10 to the negative 4, and the other one will be negative 0.019. And we're going to use the positive one so that it could be 5 minus x. This will change our values to 3.74 times 10 to the negative 4, and our other values to 4.99 at equilibrium. Now, although we have different product and reactant concentrations, we can do a quick math to check if the K value for each is the same. So once we put the products over the reactants, we'll find that both have the same K value of 2.8 times 10 to the negative 8, which is the same as our original K value, meaning that no matter what, the equilibrium constant will remain the same even though we may have different concentrations. Take 1 second to pause and try to think if you can think of any chemical equilibriums in your day-to-day life. A good example I like is fizzy soda. In the actual drink, there is liquid carbon dioxide. However, there's also CO2 gas in the space between the liquid and the cap. Here I didn't draw a cap, but just pretend it's a bottle. I'm not good at drawing. There's constant movement of CO2 from the liquid to the gas phase, and from the gas phase into liquid. And this is an equilibrium that maybe we can't see, but is still happening. Alright, I think you're ready to try one on your own. Let's say that a chemist mixes 2 bar of CO with 2 bar of H2O, producing 0.5 bar of H2 and 0.5 bar of CO2. And let's say you know that the equilibrium constant is 1.0 at 1100 Kelvin. Now, using this information, can you calculate the equilibrium pressures and determine which will have more, the products or the reactants? Take a minute and pause the video, and then unpause when you're ready to see the solution. Alright, so what I'm going to do is first write out the balanced chemical equation, just like before, and then make an ice table. I'm then going to fill in the pressures that we know and write out the change so we can write out an equilibrium expression. Now we know what the K value is. It's 1, which makes our lives a bit easier today. we can write out the products over the reactants and know that this will equal 1. Now what I'm going to do is multiply the expressions by each other in an attempt to isolate x. And this will be done by using the FOIL technique, first, outer, inner, last. And this will leave us with an expression kind of like this. And then what we are going to try to do is isolate x by putting 0 on one side and all the other expressions on the other. And once we figure this out, we can end up with a simple equation that we can easily isolate x for. In this case, we found that x equals 0.75, and we can go back and plug these into our equilibrium expressions to find out what pressures will be present at equilibrium. In this case, all of them will end up being 1.25 bar. And this is a coincidence. They could be different. So in this case, all the products and reactants are present at equal amounts at equilibrium. Well, that's it for me. Thanks for joining me today, and I hope you learned something.